Oxidation numbers. We may already be familiar with this, but as a useful review, we'll go over the rules of assigning oxidation numbers as a quick refresher. So, first off, any pure element that is an element all by itself, such as H2, that is a pure element, it comes as a diatomic, or iron metal, has an oxidation number of 0. That is because it's neither going to unequally share electrons, or it just has all of its electrons available to it. Now, next on the list is a single atom ion, like S2 negative. S2 negative sulfur sulfide has a oxidation number of -2. And any single atom ion, so just one atom in the ion, the oxidation number is the charge on the ion. So if we had, say, sodium plus, that would be +1. All right, those are the easier to determine things because it's generally either written right on there or, in the case of a pure element, implied to be 0. Now let's talk about the rest of the rules. Anytime we have a fluorine in the sample or in a compound, its oxidation number will be -1. Fluorine is the most electronegative element and it wins in that tug of war, so it's always -1. Now, oxygen is almost always -2. Now, there are a few exceptions to that rule, and that would be when it is bonded to a fluorine, it may have a different oxidation number. For example, if we, instead of the compound like water, H2O, we had F2O, so oxygen with 2 fluorines on it. Going by our rules of fluorine is always -1, this would be -1, that would be -1. And since this is overall a neutral compound, we'll get to that rule in a minute, but the oxidation numbers have to add up to the charge of the compound or ion. And since this is 0, this must be +2 because that will now add up to 0, which is the charge of the overall molecule. So in this case, oxygen is quite a high, has quite a high oxidation number. And that is simply because the fluorines are -1s. Another time when oxygen will deviate from this -2 is when it's in a peroxide compound. So let's take hydrogen peroxide. We'll have to use our next rule right here, which is hydrogen is +1 to determine this one. But we have hydrogen peroxide, right? And so in this case, we have hydrogen is +1. And since we're in a peroxide compound, the oxygens will be -1s. So instead of the oxygen being -2, now it's -1. And we can also go a step further and go into a compound that would have a superoxide. Like potassium superoxide. And in this case, the oxygen will have an oxidation number of -1/2. Because the potassium has a +1. Now, that brings up an important point. It is possible to have non-integer values of oxidation numbers. It doesn't happen that often, but it is possible to have a fractional oxidation number. Okay, so that's some of the exceptions with oxygen, but remember again, most of the time it is -2, and only when there are additional oxygens around or fluorines, otherwise known as other electronegative elements, do we deviate from this being -2. All right, now hydrogen is generally +1. There are a few exceptions to this rule, such as lithium hydride, in which case the hydrogen is the more electronegative element, and in this case the hydrogen has a -1 oxidation number, whereas the lithium will be +1. And that's just simply because the hydrogen is the more electronegative element. That doesn't happen very often, but when it does, we can have a hydride. Now, there's two other rules, and I kind of mentioned them, that you can really combine into one, and that is if we have a molecule or an ion, all of the oxidation numbers of each individual element inside have to add up to the overall charge of the molecule or ion. So let's use some examples to put that rule into practice. So up here we have an iron 2+, and so the oxidation number is simply the charge of the ion. So this is +2. And sulfide, 2 negative, so the oxidation number of that is -2. And then here we have gold solid, that's only gold. And so since it's a pure element, it will have an oxidation number of 0. Now we get into a compound, which overall has no charge. And we should remember that chlorines have a -1 charge. And that's typical for halogens to have a -1. So if these are -1 and there's 3 of them, that must mean that the cobalt is +3. So the oxidation state on the cobalt is +3. Now, here is a neutral covalent compound, and we'll have to use our rules. So overall, this thing, nitrogen dioxide, is neutral. So the total charge on this is 0. Now, we need to figure out what the oxidation number is on the nitrogen. We already know what the oxidation number on the oxygen is. It's -2 because our rules say that this is -2. And it's not one of those exceptions. So we have -2, but we have 2 of them. And so in order for that to add up to 0, this must be +4. So the nitrogen is +4 there. Now, if we move down to the nitrate anion, we have a negative charge here. So we still have oxygen, which is still -2, but we have 3 of them, so that's a total of -6. But there's a negative up here, so we need to counteract 5 of those negative charges in order for this whole thing to add up to -1. So +5. 5 minus 6 is -1. So that's where that comes from. Now we move down into the hypochlorate, or not hypochlorate, hypochlorite. Yeah, it took me a second. -2 here. Overall, -1. So we need to counteract just one of the -2's, which will lead this to be +1. So 1 plus -2, -1. All right. Now down to the perchlorate ion. Got that one right. in that case, we have still -2 for the oxygen, which makes this whole part right here -8. And we really need this to be -1, so we've got to counteract 7 of those charges, so this is going to be +7. And you can notice that when I increase the amount of oxygen in these compounds, the oxidation number of the other, the nitrogen here or the chlorine, went up. And as you should expect, that increasing the amount of oxygen on there will cause this to be oxidized. Imagine that. Now let's come up and do something that's a little bit different. Over here, these are organic compounds. Now, it's possible to assign oxidation numbers to the carbons in the organic compounds, and sometimes this is a useful thing to do, and other times it's kind of a little bit made up. And I'll illustrate how it's kind of a little bit made up with these first two compounds here. In this case, we have fluorine, which is going to be -1, and there's 4 of them, so this must be +4. Now that's a really oxidized carbon, and it is true that carbon's going to be devoid of some electron density because the fluorines are going to be pulling the electrons away from the carbon, so it will be positive, but I'm not so sure that it will be a full +4 in reality. And it probably won't act quite like it's +4. Now, if we come down to here, we use our idea that hydrogen is +1, and indeed in carbon compounds it is, because the hydrogen is a little bit less electronegative than carbon. I believe carbon's 2.5 and hydrogen's like 2.2. So we assign this +1, and since there's 4 of them, now carbon's -4. Now, in general, this is not going to act quite like its carbon is a -4. It's probably even less than this. This is a little bit more real because we have quite an electron withdrawing going on here, but this is more of a formalism rather than an actual guide. Where it comes in more handy is when we start looking at these compounds down here. This is an aldehyde. This is a ketone, an acetone. And this is a carboxylic acid, acetic acid. Right? And you'll notice that in some of these cases, we're changing how much oxygen is on there. We may be changing the oxidation state of this carbon right here, this so-called carbonyl carbon. That's the carbon with a double bond to the oxygen right there. So let's determine what the oxidation number is on this carbon in each of these compounds. Now, when carbon is bound to itself, that will have no effect on the oxidation number, so we don't have to consider the difference between anything being affected by this carbon. So we can ignore this whole part of the molecule, and we'll just focus on this part, the part that doesn't have the carbon, only carbon on it. So here we have oxygen, that's -2, just like normal. And we have a hydrogen, that's +1. And the overall compound is neutral. So in order to get a neutral compound, this carbon must be +1. So 1 + 1 - 2, 0. So this carbon is only +1. Now we drop down to here, and we still have this oxygen here, causing it to be a -2 up here. But now we have a 0 over here, and we have a 0 effect over there. And so the only thing that can counteract that -2 is this carbon right here. That's going to be +2 now. So this is a little bit oxidized from an aldehyde. And that can be a useful thing when you're trying to do a reaction, figuring out what I need to add to something to cause an aldehyde to be oxidized to something else, or what can I do to make those kinds of reactions happen. I can recognize that that's an oxidation, and I can see what I can do to make that happen. Now, if we drop down here to the carboxylic acid, this is going to be the most oxidized of all of them. There's a good hint for that. There's more oxygen on the molecule. So we look at the hydrogen. This is +1. This oxygen and that oxygen are -2s. So we have -2, -2, that's -4, +1, that's -3. So we have to counteract of -3, so this must be +3. And so you can see that this carbon right here is the most oxidized because it has the highest oxidation number. And again, a lot of times in organic molecules, it's just more important to recognize which one is the most oxidized and not rely a lot on the exact number. When we're talking about inorganic compounds, the exact number is a little bit more useful, I think, because you can use it a lot better when balancing equations and seeing what is actually happening.